So last one, what we saw that we are showing this proof that the infinite series that 1 by Pn, the reciprocal of the primes. If I take that, so P1, P2, P3, these are the prime, and Pn is the nth prime, right? So then if I take the infinite series, then it is divergent. So that is what I want to show. Right. So here we will go to the proof later, but here we actually came across something called the integral test. Right. So okay, let me tell you that first. So the integral test is, so suppose f is a continuous positive and decreasing function. Of x on the interval 1 to infinity, and suppose an is nothing but f of n. Then this series n equals to 1 to infinity, and if we compare the integration 1 to infinity f of x dx, so this either both of them converge or both of them diverge. So yes, so this is the integral test. So integral test is one of the, so when we want to show that a particular series is convergent or divergent, so we can use the integral test. So integral test is one of the test.
Continuous.
Right. Positive.
Positive. Decreasing.
Right. Decreasing function. So decreasing function we know, right? Yeah, when the value of x increases, then the function value decreases. That is a decreasing.
Yeah. In 1 to infinity.
Right. The function is defined on this interval 1 to infinity.
Yeah.
Right. So yes. So if we see one application, then we'll get an idea. So the application is, if you recall, the if we take, okay,
We can take the previous serial.
yes, that we can take. But just before that, one more thing. So if we take 1 by n power p, this is the p series, right? If you remember, n equals to 1 to infinity. This is called the p series. So the thing is,
This is what?
p series.
B serial.
Yes.
NEP.
NAP, yes. So this is the particular, this is called a p series. Then the condition is, when does it converge or diverge? So if p is strictly greater than 1, then the series converges. Right. And the second condition is, if p is less than equals to 1, then the series diverges. Okay. So this is the condition for the p series. So this is one thing, but the thing is we can easily prove it by the integral test. So just for an example, if I take p equals to 3, then our series is n equals to 1 to infinity. 1 by n cube, right? The
mm,
what is the function I can take? Function I can take is 1 by x cube, right?
mm,
That is the corresponding function, right? If you see the theorem, see the statement,
mm.
right? So this
Yeah.
function satisfies all the conditions, right? So this function is continuous, it is positive, and in this interval 1 to infinity is positive, and it is a decreasing function because it is a reciprocal function, right?
Mm,
And an equals to f of n. So this is my an, and if I put x equals to n, then I get this an. So all the
mm,
conditions are satisfied, right?
mm,
So now if I look into this series and if I look into the integration, there is the integral 1 to infinity 1 by x cube dx. So these two things either converge and diverge at the same time,
mm,
right?
mm.
So what is this integration? Can you tell me? 1 to infinity.
It's minus power minus 3, so it's minus 3
Okay.
is I don't know, integration, not derivative.
So
Or
it's
is
this.
the it's minus is minus is minus 2 is minus 2
Right.
in 1 over 2.
1 over 2.
So it minus 2
Right.
minus 1 over 2. It minus
Right. Minus 1 over 2, this thing. Right. So now we have to apply the limit. So the limit is from 1 to infinity. So at infinity it is 0, right? Because it is 1 over x square.
mm,
So the upper limit is 0 and the lower limit is half. So it is only half, right?
mm,
Correct?
1 over half minus is right.
No, no, not minus because this is the when you apply the limit, it becomes whatever this thing
Okay,
at
okay, 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 okay.
this is the lower limit. So it is already minus of minus half. That's why half, right?
Mm,
So this thing is convergent. So this has a particular value. So I can also conclude that this is also convergent. So that is how this integral test help us. Okay.
mm, mm.
So now if we go back to our thing, so what is our sequence here? The sequence we are taking here is this one. So let us see this one. So Q is P1 to Pk, if you remember. So now, so this is the product and the series that you are taking. So that is n equals to 1 to infinity 1 by 1 plus n cube. N cube. So the function here is 1 by 1 plus x cube, right?
Mm,
So it is defined on 1 to infinity,
mm.
positive, decreasing, and all the conditions are satisfied, continuous, right? So
Right.
now, what does the integration give us?
Mm. 1 is Q minus 1.
Yes.
So mm, 1 minus 1. So minus 1, 2, 1, minus, minus 1, minus 2. No, no. So
Yes.
one
So
plus
what is this
q.
integration?
One
Just 1 by x dx.
one plus is q. Yeah.
No, we will extend to that, but just 1 by x dx. What is this integration?
Oh, that should be s minus s. Yeah.
No, no, this is log x, right?
Ah, log. Yeah, yeah, log. Yeah, yeah, yeah.
Right. So this is log x.
Yeah,
So
yeah,
this will
yeah, yeah.
be.
Log.
So if I now extend to this one, so this
Mm-mm.
is if I so 1
Log of
by.
one is q. Yeah.
Right. So you have to adjust with that thing. So this is log of 1 plus x cube. But with that, I have to adjust a factor of,
Q. Yeah, we have q.
right, divided by q, right?
Mm.
Right.
Yeah, 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 yeah.
Right. So what I have is, so this is a log of 1 plus x plus q divided by q, and it is from 1 to infinity, right? So but at infinity, the log will be also infinity, right? So if I put at infinity, so this thing is actually diverges.
Log of infinity. Why
Yes,
log?
log is an increasing function, right? So
Log.
as x tends to infinity, the log x is also infinity, right?
Mm, mm, mm,
Right. So this thing diverges. So by integral test, we have that this summation is also divergent,
mm,
right?
mm. Yeah,
Fine.
yeah, yeah, yeah,
So by
yeah.
integral test, this sum is also divergent, but that is the contradiction that we got. But we got that every partial sums. So this is the partial sum, right? For n equals to 1 to r, I
Mm,
saw that all the partial sums are bounded because this geometric series I know it is bounded because it is the common ratio is t to less than 1, right?
mm, mm, mm,
So every partial sums is bounded, but the original series is divergent. That cannot be true, right? Because if every partial sums is bounded, then the series must converge. That is one
mm,
relation between the series and its partial sums, right?
mm, mm. Yeah, yeah, yeah.
Right. So that's why this is a contradiction. So contradiction to what we assume that that the series is convergent. So that is false. So this reciprocal series of reciprocals of prime that is actually diverges.
Mm.
Okay.
Yeah, yeah, yeah. Except the integral test.
Yes.
What's the other test for serial?
Uh, yes, there are many tests, right? So, for example, okay, let me think about it. Yes. So there is something called comparison test, limit test, ratio test, root test. Those things are there. Right?
Yeah, 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 yeah. Somewhere we review is
Yes,
your.
yes. So that is a part of real analysis. Did
Mm.
you do that?
We just review the
Yes,
some
yes.
concept not focus on yeah yeah.
Okay. So this is 1.6. So the next section
Mm.
is, so the 1.7 is a Euclidean algorithm. Okay. So it says that, okay, let me write down the statement of the theorem. The statement is the division algorithm. So given integers a and b with b positive, there exists a unique pair of integers q and r such that I can write A as BQ plus R, where R is strictly less than B and positive. And moreover, if R is 0, or you can say R is 0, if and only if B divides 0. So this is the division algorithm. Okay.
Yeah.
Right. So let us see the proof. So we consider a set of non-negative integers like this. So let S be a set of non-negative integers given by y such that y equals to a minus bx, where x is an integer and y is greater than equals to 0. So we find all collections of y such that y equals to a minus bx.
The set of non-negative integer given by
Right.
y equal to a minus bx.
Bx. So this is non-empty set of non-negative integers, right? This is a non-empty set of non-negative integers. So non-negative because I can choose my x such that this set is always non-empty, right? So this is a non-empty set of non-negative integers. So this imply by that well ordering that thing, that it has a smallest element, right? Right. So we assume that the smallest element is a minus b cube. Okay. So this is my smallest element. So for some x, so that x be cube. Right. So we define R to be this smallest element, a minus b cube. Okay. So then we automatically get that a equals to bq plus r, where r is greater than equals to 0, right? But that is not over because we have to show that r is strictly less than that part we have to show. And also uniqueness is also there. Two things are left. So now we show that r is strictly less than b. R is strictly less than b. So we'll assume contradiction. So assume that r is greater than equals to b.
So we have bq plus 1.
Yes, we can subtract more. So then this, if I subtract b from r, that is strictly non-negative and it is smaller than r, right? So this implies r minus b belongs to s, since r minus b is of the form a minus b of q plus 1, right? So this is a contradiction to the smallest element being r minus b, right? So there is a contradiction. So hence r has to be strictly less than. Okay. So now we have to show that this q and r, this pair is unique, right? So again we assume contradiction. So suppose q comma r and q prime r prime be two pairs. that satisfy the condition, that is A equals to BQ plus R, also BQ prime plus R prime. Okay.
Hmm.
So from here, what I have is B of Q minus Q prime, that is R prime minus R. So this implies B divides R prime minus R, right?
Hmm. Hmm? Okay, okay, yeah.
So it B divides R prime minus R. So now if this R prime minus R is not equals to 0, so this implies that B has to be less than equals to the absolute value, right?
Hmm.
But that is a contradiction, right? Because individually R and R prime both are smaller than B, right?
Hmm.
A contradiction, since this R and R prime both are strictly less than B, right?
Hmm. Hmm.
So this implies that R minus R prime has to be 0, that is R equals to R prime. So
Hmm.
once R equals to R prime, similarly we have Q equals to Q prime.
Hmm.
So hence we have uniqueness, right?
Hmm. Hmm.
Yes. No, the last part is nothing there. So if R is 0, then this is of course B divides A,
Hmm. Hmm.
and
Hmm.
on the other hand, if B divides A, R has to be 0, right?
Hmm. Yeah, yeah, yeah.
Right.
The wait. The
Yes.
construction in less than b minus b equal to a minus a
Yes. Yes.
q plus one.
Yes.
What is the contradiction here?
Yes. Yes. The contradiction is we assume that R minus this A minus BQ to be the smallest element of S, right?
A minus bq smallest. Yeah.
Yes. But with this element, this also belongs to S, right? So, but this one is strictly less than this element. So I got a another element that is smaller than this. So that is a contradiction.
Uh, yeah. But why this one belong to S?
This one belongs to S because this is of this form, right?
Uh,
This element is of this form, right? A minus bx, where x is an integer and this one is positive, right?
so why he is a minus b?
Right, right. Y is r minus b, right?
Uh, yeah.
Right.
Mm, mm,
So fine, right?
yeah. Mm.
Okay. So this is the division algorithm. Next is the next theorem is the Euclidean algorithm. Okay. So it says that given positive integers a and b, where b does not divide a, let r0 be a and r1 be b, and we apply the division algorithm repeatedly to obtain a set of remainders, say R2, R3, and so on, Rn and Rn plus 1, defined successively by the relation like this. That is R0 is nothing but equals to R1 Q1 plus R2, where R2 is strictly less than R1. Next, R1 equals to R2 Q2 plus R3, and so on. Rn minus 2 is plus Rn R of n plus 1, where R of n plus 1 is 0. So then, if I can successively define the remainders like this, then the last remainder, that is Rn, that is the GCD of this A and B. So this is the statement.
That's the algorithm to find GCD.
Right. That is the algorithm.
Just why AB. IP. Apply division.
Okay.
That's
So
it.
this is the
Wait, that's it. That's it. Q1. Where is Q1?
Q1. Q1, no, Q2.
Okay. A0 is I. Ah, okay. A0 is Q.
Yes. R0 is A and R1 is B. So I can find my Q1 and R2, right, from that. So once I find Q1 and R2, then I go to the next line. So R2 will come. So R1 will come here. So R2 will come here, right? And then I find Q2 and R3 and so on, right? So we stop at a position where this R of n plus 1 becomes 0. So then the previous step, the remainder will be my GCD. Okay.
Okay. Actually, we divide A to B and get the remain. After that, okay, okay. Yeah,
Okay.
yeah, 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 yeah,
Okay.
yeah. Okay, okay. Even though I got this, but we can demo the algorithm by some
Yes. So your voice is
a pair.
not it's low. Uh, your voice is coming very low.
I mean, we demo by a pair of number.
Yes, we will see some application. Yes, of this algorithm, right? So the statement is fine, right?
It's okay, it's okay.
Right. So proof we will skip because it is nothing, just induction. Not induction, but we step induction on n on something can apply. So that is fine. So next one is so greatest common divisor or GCD. We saw between two elements, right? So now what will happen if it is more than two members? So that is the next section. It is the greatest common divisor of more than two numbers. Okay. So suppose I have three integers. So A, B, C are three integers. Then the GCD of A, comma B, comma C. So there is nothing but A comma, so we'll take GCD of BC and then take GCD of A and that GCD of BC. Okay. So this is actually symmetric. We can do anything. So we can first do AB and then do C. So that also we can do. Right.
It's okay.
So similarly for any so similarly the GCD of n numbers or n integers, A1, A2, An. So this we can define inductively. That is this A1, A2 up to An. So that is nothing but we do up to, so A1 and A2 up to An, that we can define, right?
That is okay.
Right. So yes, also the same idea. So if we know that if A and B is 1, the GCD of A and B, so then we say that A and B are relatively prime, right? Okay.
That is okay.
So if D is 1, then we'll say this is relatively prime. So the thing is, if AI and AJ, so that is 1, whenever I is not equals to J, right? Then this will imply that this implies that the numbers are pairwise relatively prime. So that is different. So A1, A2, An, these are pairwise relatively prime. Okay, so that is different from saying that A1, A2 up to An, their whole GCD is 1. So these two things are not same. Okay. So for an example, if I take 2, 3 and 10, right? So their GCD is 1, but they are not pairwise relatively prime because 2 and 10 they are not, right? So these two things are different.
Relatively brown.
Yes.
That's a for uh, relatively brown.
Yes, relatively prime and pairwise relatively prime, these two things are different. That is what I'm saying.
Two number is prime are not need to both of them is prime.
Okay.
That relative prime is something like 2, 3
Yes, yes. 2, 3.
or
That is for
5.
two. That is for two digits. But if I have n things, then if the GCD of n things is 1, then we'll say that is relatively prime. But
It's
pairwise
okay,
relatively
but
prime is,
just the definition of relatively prime. What
yes,
does it
relatively
mean
prime is GCD is
relatively
1.
prime?
That much.
Relatively prime that mean two uh, uh, equal to one. That mean relatively prime.
Yes.
Okay.
But pairwise relatively prime means for every ij that is not equals to I not equals to j, I must have ai and aj is 1.
Yeah, yeah, yeah,
Okay.
yeah. Mm.
So this is more or less. So let us see some exercise problems now. So if GCD of AB is 1 and if C divides A and D divides B, then GCD between C and D is also 1. How will you show that?
maybe one and equal to three.
Right.
Three equal to one. Hmm. 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 Yeah, yeah, yeah.
So how will you show that?
It's okay, but I am considering that if A, B equal to one, so A and B both are prime, is right?
No, no, not both are
Hmm.
prime. They're relatively prime. They
For,
don't have anything common. That is what we know. The GCD
for,
is one.
for example, four, four and what?
Suppose 4 and 9 you can take, right?
Oh, yeah, 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 yeah. Okay, okay, four and nine. Yeah, yeah. Okay, okay, okay. Okay. So it should be combined from different prime, is right? For example, four is two power two,
Right,
nine is three power nine.
right,
That's
right. So
different.
they must be different. They cannot have same prime factors.
Yeah, yeah, yeah. Wow. Yeah, yeah.
So yes. So
Mm-mm.
we can actually use the Euclidean that this thing, right? So since so GCD is one, so there exist integers x and y. By equals to one, right? This you know, right?
Yeah.
Now,
One way to play it.
yes, sir.
Mm. Yeah, yeah, yeah. It's okay.
So this is on the Euclidean algorithm, right?
Mm.
So now, what I have is C divides A. So this implies A equals to some C times N, right?
Mm.
And D divides B. B equals to some D times M,
Mm.
right?
Mm. Yeah, yeah, yeah. It's
Right.
okay.
Now we can substitute that into that equation. So what I
Mm.
have C and X,
Mm.
that is one.
Yeah, yeah, yeah. We group together.
Right. So C I can take out and D I can take out. Right. So this is the equation. So from here, this implies that the GCD of C and D has to be one, right? Because nx and my these are integers, right?
Mm.
Okay.
Yeah, yeah, yeah. It's okay.
Right. So next one is suppose you have a comma c, that is GCD of a and c, and a and b both are one. Then the GCD of a and bc, that is also one. How will you show that?
I see. I see. One.
Yes,
Then.
both GCD is one.
Yeah. So A is 1 plus the Y1 equal to 1. Yeah.
Yes. So I can have ax1 plus by1 equals
Mm.
to 1, and ax2
Mm.
plus by2 equals to 1. So for some
Mm.
x1, x2, y1, y2 belongs to integers. Yes. So this I have then.
Oh, yeah, yeah. But the first is not B, the first is C. C.
Oh, yes, yes.
Yes.
See, yes.
Yeah. So we want to we substitute how we substitute we need to A B C
Alright, we need BC.
A B C. So 1 1 we can A is 1 but we want C. Oh wait, we need to A in B C Y multiply if we multiply is 1 A square B C Y A. Then A B C equal to 1. A B C equal to 1. Here we have A. It one B1. It one is 2. Oh.
Yes. So now we can multiply these two things together, right?
Yeah, maybe we multiply we have A square and BC.
Yes, but that is not a problem. Let us see. So this is
Oh.
one. So now if I open it,
A square. It one is 2. AB it one is 2. BC.
right?
Mm.
But I can adjust, right? So I can take out a common.
Mm. Oh.
Right. So now we'll define. So these are all integers. So I
We
can
left
define this one as x
okay. Okay.
and this one as y, right? So this implies that a and bc. So
Hmm.
their GCD is also one, right?
Yeah, yeah, yeah.
Okay.
Mm. Mm.
So suppose AB is one. That is the GCD of A and B is one. Then A power n and B power k, that
Mm.
is also one. For all n comma k greater than equals to one.
Oh. Mm. So we have A is plus BY equal to 1. But
Yes, but that will not help, right?
no,
Because
yeah,
the power
yeah,
is very high.
yeah, yeah.
So we have to go by some contradiction, right? So suppose the GCD is not one, then suppose
Mm.
P is a common prime factor. Suppose P divides A power n and P divides B power k, right? For some prime P, right? So we are assuming contradiction that the GCD is not one. Then some prime should divide, right?
We spot we have some common
Prime factor, right?
better.
So now, if P divides A power n, then P must divide A also, right? Because it is a prime factor, right?
Mm. Mm.
Right.
Yeah. Yeah.
And P divides B also, since P is a prime. So this implies
Mm.
that P divides the GCD of AB, right? So which is a contradiction because the GCD of AB is 1. So they cannot have a same prime factor. Okay.
Mm. Mm. It's okay.
So if the GCD is 1, then the GCD of A plus B and A minus B, so that is either 1 or 2. So either they are coprime or maximum the GCD will be 2.
Mm.
So how to show this one?
A plus B, A minus B.
Right.
Oh, A plus B, A minus B. A plus B, A minus B, A plus B. So we can A plus B, A minus B. So we can assume that A plus B equal to A minus B multiplied U plus R is right.
Okay. So
And we have to prove that R equal to 1 or 2. What's or A is plus
yes, I will
B,
do that.
A plus BY equal to 1. A plus BY equal to 1. A plus B, A plus B, then A plus
So here actually we can use the traditional one. So AB is 1, right? So this implies there exist integers x and y
AB plus 1. Mm.
such that ax plus by is 1, right?
Mm.
Okay.
But A plus B, A minus B.
Yes, that will come. That will
Mm.
see what will happen. But
Mm.
the thing is, now we have to use this one. So with a plus b, if I take x plus y, and with a minus b, if we take x minus y, right? So then I have ax plus bx plus ay plus by, right? Ax minus bx minus ay plus by, right?
Mm.
So now what I'll have is ax plus by is 1, right?
Mm.
And similarly, what else we have? So bx will get cancelled, ay and ay will get cancelled, right?
Mm.
So I have 2 times of ax plus 2 times of by, right? So that is 2.
Mm.
Okay. So this implies that the GCD of AB and A plus B a plus b and a minus b, that is at most 2, right? Because so this is my new integer x and y, so that I am getting 2, so it has to be less than equals to 2,
mm,
right? So it is either 1 or 2.
mm. But the boy, he is y a plus b s plus y come out. Yeah.
Yes.
Mm. Y is come out a plus b.
So
Mm,
I got a linear combination of this a plus b and a minus b. This is my new number. Maybe you can say m and n, such
mm,
that it is equals to 2, right?
mm,
So the thing is, GCD has to be less than equals to 2, because suppose D is the GCD, right? So D
mm,
is the GCD, and then D divides this one and this one, right?
mm,
So if D divides this one, then D should divide this one also, because D divides this and this. So D divides 2, right? So D has to be less than equals to 2, because the
mm,
divisors are less than equals to 2.
mm, mm,
So that's why it is either 1 or 2.
mm,
Okay,
mm. Yeah, yeah.
fine, right?
Yeah, but I can feel about the way a pro is come out is not naturally because we don't know we should start from a plus b multiply with s plus y
Yes,
plus
yes. The thing is, the only idea is to why did we start like this? So that is, we have to use this result, right? So if I take x plus y with a plus b and x minus y with a minus b, then the things get cancelled out. So that's why.
mm, mm, yeah, yeah, mm,
Okay.
mm.
So today we'll stop here then.
Yeah, yeah, it's